Today, we're stepping inside Prakash Steel Products Limited, one of India's respected steel manufacturing companies, to see exactly how modern steel products are made from start to finish. And trust me, this process is as impressive as anything you'll find on a factory floor in Pittsburgh or Gary, Indiana. It all starts with raw material selection. At Prakash, the process begins with carefully sourced steel billets and scrap metal that meet strict metallurgical standards. Quality control isn't an afterthought here, it's baked into every single step from the very beginning. Next comes the melting and refining stage. Steel scrap is loaded into a high-powered electric arc furnace, or EAF, a massive machine that generates temperatures exceeding 3000 degrees F. Inside that furnace, powerful electrical arcs melt the steel down into a molten bath. This is where the magic really begins. The liquid steel is then transferred to a ladle furnace for secondary refining, where alloying elements like manganese, chromium, and silicon are added to achieve the exact grade and specification required for the final product. From there, the molten steel flows into the continuous casting machine. This is one of the most fascinating pieces of equipment in any steel plant. The molten metal is poured into water-cooled copper molds and solidifies progressively as it moves downward through a series of rollers, emerging as a long, solid steel strand called a billet. These billets are then cut to length using automated flame cutters, still glowing red from the heat. Now comes the rolling mill, and this is where things get really exciting. The hot billets are reheated in a pusher-type reheating furnace to around 200 degrees Fahrenheit to restore their workability. Then, they're fed through a sequence of rolling stands, pairs of grooved rollers that progressively squeeze and shape the steel into its final cross-section, whether that's rebar, angles, channels, or flats. Each rolling stand reduces the cross-section a little more, elongating the billet and refining its shape with incredible accuracy. The whole thing moves at speeds of up to 18 meters per second. That's fast enough that you'd barely see it if you blinked. After rolling, the steel goes through quenching and self-tempering, a controlled cooling process that gives the finished rebar its signature combination of a hard outer surface and a tough, flexible core, essential for reinforced concrete construction. Finally, every product goes through final inspection and testing, dimensional checks, weight verification, and mechanical testing, including tensile and bend tests, before being bundled, tagged, and shipped to construction sites and fabricators across the country. Today, we're pulling back the curtain on GMW, a company at the cutting edge of automated electric motor production equipment, and the technology they use is something that would have looked like science fiction back in the 80s. GMW specializes in designing and manufacturing automated production lines for electric drive motors, the kind found in EVs, industrial machinery, and high-performance applications. Their systems bring together robotics, precision mechanics, and intelligent software in a way that's genuinely remarkable to watch. The process starts with stator core lamination assembly. Electric motors require a stator, the stationary part of the motor, built from hundreds of thin, precisely stamped silicon steel laminations, each just 0.35 millimeters thick. GMW's automated stacking systems align and press these laminations together, with tolerances measured in microns. From there, the line moves into coil winding. This is where copper wire, sometimes as fine as a human hair, is wound into the stator slots in very specific patterns. GMW's CNC winding machines can handle both round wire and flat wire. Hairpin winding, the latter being the preferred method in modern high-efficiency motors because it achieves a higher copper fill factor, meaning more power from a smaller package. The machines wind, cut, and form the coils automatically, with each step monitored by sensors for tension, alignment, and positioning. Once winding is complete, the stators enter the insulation and varnishing station. Here, the wound stators are coated with a specialized varnish or epoxy resin using a vacuum pressure impregnation (VPI) process. The stator is placed in a vacuum chamber which pulls out all the air from between the windings. Then the chamber is flooded with resin under pressure, ensuring every gap is completely filled. Next up is rotor assembly. GMW's rotor lines handle the pressing of permanent magnets into the rotor core, followed by precision dynamic balancing. An unbalanced rotor, even by a few grams, can cause vibrations that shorten bearing life and generate noise. The balancing machines spin the rotor at high speed, detect the imbalance, and automatically remove tiny amounts of material from specified locations until the rotor spins perfectly smooth. The final stage is motor assembly and end-of-line testing. Stator and rotor are married together, bearings are pressed, end shields are bolted, and the completed motor goes straight into a fully automated test bench. There, it's put through its paces: no-load testing, loaded performance curves, insulation resistance checks, and vibration analysis, all in just a few minutes. Any motor that doesn't meet spec gets flagged automatically and pulled for review. Today, we're watching the complete machining of a two-cylinder engine crankshaft on the Niles N20 MCX 2000, a 5-axis CNC turn mill center that represents the absolute pinnacle of crankshaft machining technology. The Niles N20 MCX 2000 is built by Niles Simmons, a German machine tool manufacturer with roots going back to 1858, older than most American states. The N20 MC is a 5-axis horizontal machining center with an integrated turning spindle designed specifically for complex rotational parts like crankshafts, camshafts, and axle shafts. Now, the process. It begins with the raw steel forging, a rough, oversized blank that's already been heat-treated to the correct hardness before it even reaches the machine. The blank is loaded between centers and clamped. First operation: rough turning of the main journals, the central bearing surfaces that sit in the engine block. The machine takes aggressive cuts, removing material quickly but deliberately, leaving a controlled amount of stock for finishing passes. Next come the pin journals, the eccentric bearing surfaces that the connecting rods attach to. This is where 5-axis capability truly earns its keep. Because the pin journals are offset from the rotational center of the crankshaft, the machine must synchronize rotation with the cutting tool's radial position in real time, a technique called contour turning or orbital milling. The cutter follows the pin journal as the crankshaft rotates, maintaining perfect contact throughout. After the journals are roughed, the machine switches to milling mode for the oil hole drilling and counterweight profiling. Oil holes are drilled at precise angles through the crankshaft. These passages carry pressurized oil from the main journals to the pin journals during engine operation. The counterweights, those heavy lobes you see flanking the journals, are then contour milled to their final profile. Their weight and position are engineered to cancel out the vibration caused by the rotating and reciprocating masses of the pistons and connecting rods. Now comes the most critical phase: finished turning and grinding. The journals are finished turned to within a few microns of their final size, then handed off to precision cylindrical grinding for the final surface finish. Finally, the crankshaft goes through CMM inspection. A coordinate measuring machine sweeps across every critical dimension, verifying journal diameters, roundness, straightness, and the angular relationship between each pin journal. What you're watching is the UGS61A, a CNC hydraulic pipe bending machine designed for bending steel tubes with wall thicknesses up to 6 mm and diameters ranging from small bore lines up to industrial pipe. This machine is widely used in HVAC fabrication, automotive exhaust systems, structural frames, and hydraulic line manufacturing. The process is straightforward but precise. The tube is loaded into the machine and clamped between a bend die and a clamp die. A mandrel, a flexible steel rod, is inserted inside the tube to support the wall from the inside during bending, preventing collapse or wrinkling. Then the pressure die locks against the outside of the tube, and the bend arm rotates to the programmed angle. The UGS61A can execute multi-radius, multi-angle bends in a single setup, with repeatability within plus or minus 0.1 degrees. Every bend is controlled by the CNC unit, no guesswork, no manual adjustments between runs.